start to take a look at the geometric shapes called polygons. If you look at the Common Core State Standards, you'll see that geometric shapes like polygons are mentioned all the way back in first grade. And in fact, all the way through the elementary years, polygons are addressed in the Common Core State Standards. We're going to draw some polygons and look at some definitions associated with them. First of all, a curve is a path drawn without lifting the pencil. So this would be an example of a curve. This also is an example of a curve, but it's called a closed curve because it can be drawn by starting and stopping at the same point. This is an example of a simple curve because it's a closed curve and it does not cross itself. And this is an example of a polygonal curve. That's a curve that's made up entirely of line segments. A simple closed curve, like these two, are called concave if a line segment whose endpoints are inside the curve contain points which are outside the curve. In other words, if we can draw a line segment on this figure that has endpoints that exist within the inside of this closed curve, and any part of that line segment is outside of the closed curve, then we have a concave polygon. This one's also concave. See how we can draw a line segment that has endpoints in the curve, but it also has points outside of the curve. Now, if a simple closed curve is not concave, then it's convex. And convex means that no matter what line segments we draw that have endpoints inside the curve, every other point on that line segment will also be inside the curve. This is a convex polygon. We could draw a line segment anywhere inside this figure, making sure that its endpoints are inside the figure, and all the other points on that line segment would also be inside the figure. So let's look at these 5 shapes, and let's decide whether each of these shapes is a curve, or if it's closed, or if it's simple, or if it's polygonal. So we'll start with the one on the left, the yellow one. It is definitely a curve. It is not closed. We can't draw it by starting at one point and then ending at the same point without lifting our pencil. It is simple, but it's not polygonal. It's not made up of line segments. Now let's look at the one next to that. It is a curve, and it is closed, but it's not simple. It crosses itself. And it's not polygonal because it's not made up of line segments. How about the red one? It is a curve, it is closed, it is simple, but it's not polygonal. It's not made up of line segments. The fourth one, it is a curve, it is closed, it is simple, and it is polygonal. And the last one, it is a curve, it is closed, it's not simple because it crosses itself, but it is polygonal. It's made up of line segments. Now, if we have a simple closed curve, we can also ask whether the simple closed curve is concave or convex. So for the red one, it would be concave, because if we would draw a line segment that had endpoints contained within this simple closed curve, we could also have that line segment have points that were outside the curve. And the green one is convex, because we could draw line segments that have endpoints inside the curve, and all of the points of the line segment would be inside the curve. We can give names to polygons based on the number of sides or vertices that it has. the number of sides and the number of vertices will be the same. So, let's say we have a polygon with 3 sides. That would be a triangle. 4-sided polygon is a quadrilateral. 5-sided polygon is a pentagon. 6 sides gives a hexagon. 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides is a decagon. So you can see that the prefix is telling us something about the number of sides and the number of vertices. Now we can generalize this for sides greater than 10, although polygons with sides greater than 10 do have specific names, but we're going to just generalize this to say any polygon that has more than 10 sides we'll just call an n-gon. So if we had a polygon with 27 sides, we would call it a 27-gon. A regular polygon has congruent sides and congruent angles. Congruent means that the measures are the same. So we could draw a regular hexagon. That would be a 6-sided polygon that has sides that are all the same length and angles that are all the same measure. Now compare that to this hexagon. It's still a hexagon because it's a polygon with 6 sides, but those sides are not all congruent and the angles are not all congruent. We can still call it a hexagon, but it's an irregular hexagon. If we want to show in our illustrations that we have congruent sides, we can mark the sides with tick marks. If the tick marks are the same, then we're indicating that the sides are the same length. And we can also indicate that the angles of a figure have the same measure by marking them with the same tick marks. So let's continue to talk about this hexagon. What if we wanted to know how many diagonals the hexagon has? Well, we could think about the fact that there are 6 vertices on this hexagon. And from each vertex, we could draw 3 diagonals. So for example, from this vertex, we can draw 1, 2, 3 diagonals. So we can't draw a diagonal to a vertex itself, and we can't draw a diagonal to the vertex on the left and on the right. We can draw diagonals to every other vertex. Now there's 6 vertices, so from each of the 6 vertices it seems like we should be able to draw 3 diagonals. But that would be counting every diagonal twice, because we would be saying, for example, if we draw a diagonal from the one that we are now drawing diagonals on, start again. 5, 4, 3, 2, 1. So let's see if we can find how many diagonals this hexagon has. There are 6 vertices, and from each vertex we could draw 3 diagonals. Because we can't draw a diagonal to the same vertex, and we can't draw a diagonal to the vertices on either side of that vertex. And we could repeat that for each of the 6 vertices. So you might think that we have 6 vertices, we can draw 3 diagonals from each vertex, so that should be 18 diagonals. The problem with that is we're actually double counting. We're counting every diagonal twice. Take a look at that diagonal that we've drawn that's on the far left. Right now we're drawing it from the bottom to the top. We could also draw it from the top to the bottom and it would be the same diagonal. So if we say there's 6 vertices and from each one we can draw 3 diagonals, we actually are counting every diagonal twice. So the number of diagonals that we would have in this hexagon is 18 divided by 2 because we've double counted, which is 9. So there are 9 diagonals in this hexagon. Let's draw them in. That's 6, 7, 8, 9. There's our 9 diagonals. How about a decagon? How many diagonals would that have? Well, we know that there are 10 vertices. And how many diagonals can we draw from each vertex? We can't draw a diagonal to the vertex itself. We can't draw a diagonal to the vertex on the left or the right. So that means from each vertex we can draw 7 diagonals. So you might think, all right, 10 vertices, I can draw 7 diagonals from each vertex. 10 times 7 is 70. There must be 70 diagonals. But remember, that's double counting all of the diagonals. So the number of diagonals is actually half that, which is 35. We can give triangles names based on either the angles or the sides. If we name a triangle according to its angles, we can call it acute. If all of the angles are acute, all the angles measure less than 90 degrees. We can call it right if it contains one right angle, and we can call it obtuse if it contains one obtuse angle. Now we could also name triangles according to their sides. We could call a triangle isosceles if it has at least 2 congruent sides. We could call it scalene if it has no congruent sides. And we could call it equilateral if it has 3 congruent sides. So when we name a triangle, we can actually name it in 2 ways, by the angle measures and by the side lengths. Quadrilaterals are named according to sides and angles as well. A square is a quadrilateral with 4 congruent sides and 4 right angles. Now, because it has 4 congruent sides and 4 right angles, it has some other properties as well. The opposite sides are going to be parallel, and the diagonals are going to be congruent. Another quadrilateral is a rhombus. A rhombus has 4 congruent sides. Sometimes people think of a rhombus as looking kind of like a squished square, although a rhombus could have 4 congruent angles. It just doesn't have to have that, but it must have 4 congruent sides. Now, because of that, a rhombus will also have opposite angles that are congruent and opposite sides that are parallel. A third type of quadrilateral is called a rectangle. A rectangle must have opposite sides that are congruent, and it must have 4 right angles. Now, because it has those 2 properties, it also has opposite sides that are parallel. A parallelogram has opposite sides that are congruent and opposite sides that are parallel. A trapezoid has at least 1 pair of parallel sides. An isosceles trapezoid has exactly 1 pair of parallel sides and 1 pair of congruent base angles. It will also have 2 congruent non-adjacent sides. So in this case, that would be the side you see on the left and the side you see on the right. A kite has at least 2 distinct pairs of consecutive congruent sides. In other words, take a look at this figure. Those 2 sides that are at the top, they're consecutive because they're connected to each other and they're congruent. See the 2 sides closest to the bottom? They're consecutive because they are connected to each other at a vertex, and they are also congruent. So that's our 2 pairs of consecutive congruent sides. So think about this figure. What would the best name be for this figure? Well, the best name is a rectangle. It has 4 right angles and its opposite sides are congruent. But what other names could we give it based on the definitions we just talked about? Well, it could be called a parallelogram because a parallelogram has opposite sides that are congruent and opposite sides that are parallel. We could also call it a trapezoid because a trapezoid has at least one pair of parallel sides. Or we could call it an isosceles trapezoid. And of course, since it has 4 sides, it could be called a quadrilateral. And all quadrilaterals belong to the family of polygons. How about this shape? What's the best name for it? Well, the best name is a parallelogram. It has opposite sides that are parallel and opposite sides that are congruent. Are there any other names we could give this? Well, we could call it a trapezoid. It has at least one pair of parallel sides. We can call it a quadrilateral because it has 4 sides. And we could call it a polygon. Now, if you take a look at page 703 in your book, you'll see a nice little chart that talks about the hierarchy among polynomials. And it will help you to see that when we look at these polynomials, there's always going to be one best name we can give the polynomial, but there's also going to be some other names that we could give the polynomial, which would be valid names for that polynomial. So that's the end of our discussion of polynomials. We have a lot more definitions that we need to remember in this particular video. Please take a look at that hierarchy chart and see if you can look at the relationships among the different types of quadrilaterals.